All right, let us get started. Good morning. So this presentation, we talk about quality of service and how various techniques are used to control traffic. So why do we need quality of service? What's basically the minimum requirements to support voice, video and data? How we use different algorithms to handle queuing. We have a couple of different quality of service models. And then lastly, we'll finish up with implementation techniques. So why do we need quality of service? We need this so that we can have a mechanism that allows us to prioritize traffic. Now, this queuing system allows us to serve a specific type of traffic more often than others. So it's a gradient of service, if you like. One of the things it also allows us to handle is areas that cause congestion. So when we have aggregation occurring, we'll get traffic buildup. So we can service the congestion in a controlled manner by applying our policy rather than just allowing it to randomly drop packets. Next is where we have a speed mismatch. Now, going from 1,000 megabits per second to 100 megabits per second is a problem because we are receiving traffic 10 times faster than we can get rid of it. So this causes all sorts of issues with what traffic do we hang on to, what do we drop. So, I mean, it's not an issue going from 100 to 1,000 because, you know, it's not going to be an issue. So, next topic will be delay or latency. This is the time it takes to get from one source to a destination. So there are various fixed points within this time frame. So the processing of the data from the media, so getting from point A to point B on any specific media adds a delay. Picking it up from one cable segment and putting it through the switch and putting it onto another cable segment adds delay. And if it's got to go through a router, that too adds delay. Now, some of these can be fixed and will be consistent throughout all versions of the packet coming down. Other times we'll have a variation. Now, when we have variations in the delay between one packet and another traveling the same path, we call this jitter. So we've got a little table there that lists all sorts of different elements that add to this delay. Now, I'm not going to read them all out to you. I'll let you read the table by yourself. The basic principle is without quality of service, our time sensitive or our voice and video will be dropped with the same frequency as the other types of traffic. So when we get real-time protocol, or for whatever service it is carrying, VoIP, video, we try to compensate for any jitter that is encountered using a playout delay buffer. So basically what this is it receives it and puts it in the buffer and then sends it on at a more consistent, steady stream. This way the spacing between the packets is more even and allows us to receive it all in a timely manner. Now, if the delay is so large that we basically cannot have it in the buffer anymore, we end up dropping that packet. So these will be heard, potentially, depending on the codec and how sensitive your ears are. So for a small one packet loss, the digital signal processor will tend to make up the difference so that the user cannot tell the difference. But if it outstrips the delay buffer and the DSP, then your audio is going to be heard to skip. So we need some form of mechanism and control over what's acceptable. So we need to set the parameters so we've got a good chance of evening out the score. So we need to have predictable bandwidth. We need real-time traffic to get priority. And data can be bursty. In other words, it can be fairly low grade and then just have a big burst with a large file that is suddenly being dropped on, which can consume all of the available bandwidth. So as video and voice traffic becomes more and more important, we have started to take steps to level the playing field. So the statistics is video traffic accounted for 70% in 2017, and they project by 2022 that it will be up to 82% of all traffic. Mobile will be basically 61 exabytes per month by that same time. That's a lot of video traffic. So we need to get this traffic put into queues first because it's real-time sensitive traffic, and this allows us to minimize the latency, the jitter, and any losses without noticeable effects to the user. Jitter should be no more than 30 milliseconds with an overall packet loss of no more than 1%. Voice traffic requires at least 30 kilobits per second of bandwidth, depending on the codec in use. And the overall latency end to end should be no more than 150 milliseconds. So this will give us smooth, benign traffic. Okay. And the user won't notice any variations. Whereas video, well, we have a little bit more variance capability within it. We can have 33 milliseconds as a baseline, but really Jitter can be a lot more flexible. We can have 30 to 50 milliseconds and an overall latency of between 200 and 400 milliseconds. The reason we can do that is because videos buffer. So it's much more flexible in its delivery criteria. We still want less than 1% of overall traffic drops, but the bandwidth requirements for video traffic is much higher. It needs a minimum of 384 kilobits per second, going up to 20 megabits per second, again, depending on the codec being used. So data. What are the characteristics of data? It can be smooth or it can be bursty. It can be benign or greedy. It can be insensitive to drops and delays because it has the ability for retransmission of those dropped or delayed packets. So, do we really need to worry about the quality of data transmission? Well, it depends. If the data is a response to an interactive application, then we could benefit from a delay minimization technique. Whereas if it's not interactive, it really doesn't matter if it gets there in half a second or 20 seconds. So what we have to do is work out what traffic policies we want to put in place. After we work out what types of traffic we want to have into order of service, then we can think about implementing a policy for queuing. Now, there's quite a number of algorithms that allow for queuing. There's first in, first out, weighted fair queuing, class-based weighted fair queuing, and low latency queuing. Now, all of these have a slightly different way of handling traffic. So basically our first in, first out is our standard everyday traffic management. So what this does is it allows us to just have normal traffic, no quality of service. Weighted fair queuing, it basically splits up and allows service between all the queues, and it's weighted based on its class. So it basically spends a little bit more time on high, a little less time on medium, normal amount of time on normal, and low amount of time of low. What does this mean? It means packets do not spend as much time in the queue in the high queue. So what this means is the traffic goes into their specific queues and we allocate a ratio of bandwidth for each queue, and that is relative to each other. Class-based weighted queuing is an extension, if you like, of weighted fair queuing. Now, we define the traffic based on not just protocols. We can have access control lists to match in certain criteria that allow us to sort the traffic into those queues. And we can then basically have first in, first out queuing on each class. Okay, but we have characteristics assigned to each class, such as bandwidth, weight, maximum packet limit, and this basically gives us a guaranteed level of bandwidth per queue. All right, so how this works is the traffic comes in and is sorted into its classes, and based on its class, it is then sent out of the egress port. So a packet that arrives last might actually be sent out first. Now, if there is no congestion, then queuing doesn't pay a great deal of impact on the whole forwarding decision. All right. If we get to the stage where all of our queues are full, then we start tail dropping. Tail drops discards packets that arrive at the tail of a queue that is completely full. All right. So if we have major congestion, it's really not going to make much of a difference, because as things arrive and all our queues are full, the traffic's going to get dropped regardless. But you've got a better chance of conserving the packets from class 1 than you have of class 3, because it will serve class 1 more often than it will serve class 3. Low latency queuing brings a strict priority queue to the class-based system. So what this does is it has the VIP queue. So traffic designated for the VIP is always serviced. All right. So the priority queue must be empty before any of the weighted fair queuing is serviced. This gives a very differential treatment to that priority queue. And it's only recommended for voice traffic. So when we implement our services on our devices, we can have either IntServ or DiffServ. So what's the difference? Integrated service provides high quality, guaranteed delivery. All right. So it's very resource intensive and doesn't scale very well. Whereas differential service is less intensive as far as resources, which makes it vastly more scalable and flexible solution. So can you have both of these services deployed within your network? Yes, you can. You can mix and match as required. But you'll get differing results because you're putting in different methods of handling congestion. Best effort. Well, this kind of is the default. All traffic's treated the same. So this is our default method of delivery. So this is the easiest quality of service to implement. It's best effort, which means there's no quality of service. Moving on. So with the integrated service, we have explicit ways of managing our resources to provide our quality of service based on individual flows or streams, and we can reserve the resources we need to provide that flow throughout the network. Now, this is a connection-orientated approach, and this is why it consumes resources, because you go through and reserve the queues or the devices and the bandwidth for the flow. Whether or not the flow is using the entire resources required or not, it's just a dedicated reservation for that conversation. If the resources are not available from endpoint to endpoint, then it doesn't allow the traffic to go through, basically. That's one of the downsides they don't promote. Now, obviously, because of this resource reservation system, it's very resource intensive because every device is communicating along the full path, and it's got to be established before traffic can start flowing along that reservation. Okay, so it requires a lot of administrative overhead to establish and maintain, and it doesn't scale very well into complex networks. And you have a lot of loss of bandwidth based on it. Whereas differentiated services does scale well because it isn't reserving resources all the way through your network. So the host forwards its traffic into the network, and each individual device applies its quality of service policy and enforces that policy on a hop-by-hop basis. Now, hopefully, this is uniform policy throughout your network, which it should have, but this allows you to have a flexible and scalable solution because it is implementing it on a first device basis. So as the packet arrives, that's when it's getting the queue service applied. So you don't have to have this end-to-end solution in place before your traffic can flow. It just gets put on the wire, and you trust the policies that you've already implemented within your entire network to handle it. So the traffic's divided in its classes based on your policy, and each of those classes of traffic is given its level of service. Now, you can choose many different levels of service under the differentiated service model. So it is a little bit more complex to set up, in that you've got to go through and set it up on all your devices and keep track of what is being done. There's no absolute guarantee for that individual conversation to have all the service provided at exactly the right time. But this is the most scalable solution and allows us the most flexibility of policy throughout the entire network. So packet loss is the result of congestion 90% of the time. As TCP experiences slowdown, it automatically adjusts the flow. Now, these sessions go up and down, and it takes applications by surprise, I suppose. The way we can prevent this is to increase capacity. Now, that's not always an easy implementation. Guarantee enough bandwidth and enough buffer space throughout the network for all. Yeah, we can do that. Or we can implement appropriate policies and queuing techniques that prioritize and forward our time-sensitive traffic, allowing our time-sensitive or drop-sensitive applications to have interrupted traffic. By dropping our lower priority data when congestion occurs, what this allows is for TCP to pick up those lost packets as part of its mechanisms and to resend them. And our drop sensitive or time sensitive applications get their information in a timely manner. So, what tools do we have? Well, we've got classification and marking tools. These analyze the traffic and assign them to a class of traffic. This is based on our policies. Then we have congestion avoidance tools, which are our applied policies. So how we apply our queues, how we decide to process, assign bandwidth, what to do when overflows occur. Okay. And then we have congestion management tools. So these are basically congestion-based tools in operating systems, and these are our class-based weighted fair queuing, low latency queuing algorithms. So basically how we approach that. Because if you remember, I said queuing mechanisms only really come into play when we start getting congestion occurring. If we've got no congestion, we're not really going to have a great deal of impact with our quality of service. Yes, it'll come through, it'll classify, it'll mark the traffic, we'll apply the policies, and we'll make our forwarding decisions based on those policies. But if we don't have any congestion, it doesn't really have an impact. Now, cast your mind back to when we did ACLs. We could apply them in both the inbound and outbound. So guess what? We can apply quality of service in both directions as well. So what type of quality of service would we apply outbound? Well, if we're facing our ISP and we have a maximum limit of traffic that is allowed out, then we want to apply policing on the traffic so that we do not exceed our upper limits. Because basically if we exceed our upper limits, one of two things will happen. We'll be charged exorbitant prices for the burst traffic, or it'll be dropped. So what we want to do, if it's going to be dropped, we want to drop it in our network where we can ensure that the messaging comes back to the source to resend that information. And it also reduces our costs, which is always a big thing as far as management's concerned. So classifying traffic flows is kind of dependent on what layer our quality of service is using. We can use layer 2 or layer 3. We can also apply filters based on class maps, ACLs, and I'll give you a hint, class maps and ACLs. And they're different versions of the same things. You're basically setting up a big filter. Okay, after you get past doing the basic routing and routing protocols, the rest of our time is basically filtering traffic to make it behave in the manner that we want it to behave. So we have lots of names for different types of filters, but they're all basically filters. What we're trying to do is separate the traffic and make it behave in a manner that we want it to. We can also classify it based on its application. So this is NBAR, Network-Based Application Recognition, which uses the upper layers of the OSI model to identify the applications in use and apply the classification. When we're looking at the classifications, we can look at how we're going to do it. Now, what we call marking is dependent on the quality of service tool being applied, what layer we're working on, and what marking field we're able to use. So as you can see from this little table, we have multiple layer 2 tools for the various technologies that we can apply, and depending on the technology, depends on what field we can use for quality of service. Now, Wi-Fi and Ethernet used to be just known as class of service. Okay, so as the times come past, we now have Wi-Fi traffic identifier, which used to be the class of service field. They've just renamed it. Then we go up into our IP traffic, and we've got IP precedence and differentiated service code point. Now, differentiated service code point has 6 bits compared to 3 bits for everybody else. So we have many more combinations available to us in this one. But guess what? We've got to sort of try to make it backward compatible. So that makes it a little bit more interesting. So when we start doing these markings, we have to insert some additional information into the headers. Remember, our overall length of frame cannot exceed a certain size, and this is why we have explicit size limitations on our data, just in case we need to turn on all the options that we want to use, we still have the space for them. So we insert two fields into our headers, and as you can see, we have the TPID, which is 2 bytes, and TCI, which is 2 bytes. All right, so we basically have pri, which gives us our quality of service. And if we have a look at how many combinations this gives us 8 combinations, and our default starts off with best effort. Strange about that. And then we come up with medium, high, call signaling, video conferencing, and a couple of upper ones that are reserved for protocol use. And apologies for my phone going nuts. The type of service or traffic class fields in IPv4 and IPv6 headers allows us that quality of service markers in IP. So this type of service or traffic class is 3 bits, and it basically tells us what we're going to use. Now, the DSCP code is 6 bits, which, if you remember your quick calculations, is 64 possible combinations. So we have a lot larger access to quality of service choices using DSCP. So our basic ones we need to sort of be aware of are best effort, which is the default, expedited forwarding, assured forwarding. Assured forwarding breaks it up into classes, and then each class has a low, medium, or high drop probability. And each one of these gives us a combination. Right. So they're worst to best case scenarios. Now, let me assure you, memorizing all of these assured values and their corresponding COS values to do a Cisco exam does one's head in. So I'm not going to worry about going through it, but basically class 1's the lowest, has the worst possible quality of service. Class 4 is the best. So as you go up in class, the better the service, and then you have low, medium, and high drop probability within each of those classes. So there is our comparison values. So as I said, class of service on the left, then DSCP values. I'll let you read and get your head around it, because you may need to read it a couple of times to get your head around it. So I'll just let you absorb it at your own pace. Just be aware that chances are you will be asked about the differences between them and some form of mapping expectation. Now, we need to classify traffic and mark it as close to the source as possible. So this means we need to define where our trust boundary is. Now, this means we have to trust the device making these policy decisions for us. So if we've got a Cisco phone hanging off an access switch, then we trust the markings from the phone because it's going to apply the marking for voice, and we want to give it priority traffic all the way from the phone through the network. Then we come up to endpoints that are marked at the switches. Now we can mark them at layer 2 switch with COS, or we can mark them at a multi-layer switch or router, depending on. So as you can see, where we decide that trust boundary has a major impact on how far the traffic travels in a best effort mode, because we cannot apply any quality of service policies until after the traffic's entered the trust boundary. We need to monitor traffic because we need to pinpoint areas of congestion throughout the network. So by monitoring this traffic, we can see any current congestions points, and we can also help to forecast potential congestion points into the future. So we can base our decisions on the average traffic patterns and what will happen if we have a spike in traffic or a sudden increase in users within the network. So we need to put in some congestion avoidance to help alleviate these problems. So we can have weighted random early detection, which allows congestion avoidance techniques on network interfaces. And this kind of helps smooth out the traffic. So what it does is it randomizes the tail dropping, maximizes network use for TCP applications. Because what we don't want to occur is for all of the conversations that are occurring into TCP to synchronize, which means they're ramping up and ramping down is all synchronized between all the conversations. So we basically get a sudden flood, sudden back off, sudden flood, sudden back off when they're in sync. By randomizing what gets dropped, we're putting different delays into each conversation, hoping that our retransmissions don't all spike at the same time, overloading the system. Shaping traffic. So the idea of shaping traffic is if we've got a mass amount of available bandwidth, what we want to do is to take all the peaks off, hold them in buffer until the trough occurs. And what this allows us to do is to smooth out the maximum traffic line to make it not exceed. So by shaping the outbound packet going through the interface, we can control our traffic so that it doesn't exceed where it's got to go. Now, shaping, I think, is better than policing. All right. So policing is what your service provider is basically going to do. Anything that exceeds the maximum information rate, in other words, the maximum bandwidth you're paying for, your service provider is going to apply a policy policing that. So as you reach your maximum allowance, it drops everything over that. So as you can see here, it is not making use of the dips in your pattern. Whereas when we shape it, we fill in the troughs, we cut off our peaks and send them in the troughs, shaping our traffic. Whereas our ISP will police our traffic and they'll just bulldoze the top of the peaks off and dispose of them. So if you're going to implement quality of service, you really need to have it so that it's from the source all the way to the destination for it to be effective. So you need to enable queuing on every device. You need to be able to classify and mark traffic as it comes into your network. And you need to shape or police traffic flows as required in the network. Now, doing this as close to the source is always beneficial, but remember, you will have congestion points where you may need to do the shaping. So remember to do any activities listed throughout the curriculum. And in summary, what did we have a look at? Well, we had a look at what quality of service was. We looked at how various mechanisms are placed within the network on routers and switches to handle how congestion can be avoided. Now, one of the things we can do is put queuing mechanisms in place so that time-sensitive traffic can be filtered out and given priority service so that they arrive in a timely manner. This minimises the delays and increases the probability of complete service. We talked about two types of delay, one being consistent, one being a variable, and we call this variance of delay jitter. And we looked at various methods that jitter can be reduced. And we stressed the main reason for quality of service was to give priority traffic, such as voice and video, a chance to get through our network. Because in the old days, we used to have segregated networks, and voice and video networks used to have their own infrastructure. So they didn't have to put up with this pesky data. We could see that data can be smooth, it can be bursty, it can be greedy, not so greedy, it can be sensitive to drops and delays. And we went through and specified the differences between voice and video for the maximum delay and maximum drop percentages, so you could see which ones had to give more priority. As voice is more sensitive than video, voice gets the highest priority whenever possible. We looked at the different mechanisms of queuing, first in, first out, weighted fair queuing, and we looked at how they apply the queuing and buffering techniques to handle congestion. Then we looked at class-based weighted fair queuing and low latency queuing, being the VIP queue of the system. So whenever something enters the allowed queue, it is immediately serviced. It doesn't wait for its share. They're the very special queue. Then we had a look at integrated service and differentiated services. We looked at the architecture that these two systems use on minimizing the delays in traffic. We looked at the quality of service tools, being classification marking, congestion avoidance, and congestion management. Then we looked at how we can classify traffic based on their layers using ACLs and class maps, or NBAR to look at the actual applications and classify them based on their applications. Now, there's an auto system for quality of service. It's basically a wizard, which is based on NBAR. The longer you can run it in its discovery mode, the better and more accurate its recommendations will be. But there used to be an entire course just on quality of service. That was a very interesting course. But we spent equivalent of one of these courses. It was 80 hours just on quality of service. So quality of service is a big thing and can be quite complex to implement correctly. We then had a look at how we can apply these filters and queues either in inbound and outbound. We talked about shaping and policing and where it's most commonly used, i.e. the interface with our service provider. And we looked at what WRED is, which is the mechanism to randomize tail drops so that we don't have TCP synchronization occurring, which can kill a network very quickly because it synchronizes all of your conversations to the same ramp up and stop sequences, which means you're in a constant flood or famine situation. That brings us to the conclusion of this morning's presentation. I have turned on the chapter exams. They're on a week. Make sure you do them. All right.